Check. Front and center.
In case you're joining us early, folks, we're just about to start, and my studio producer is just getting her equipment set up. No worries. And here we are. Good evening, everybody. I'm Derrick Pitts, Chief Astronomer at the Franklin Institute Science Museum, your cool astronomer, welcoming you to another edition of Night Skies at Home, the Franklin Institute's program that introduces you to the night sky, gives you a little bit of description about the night sky in hopes of better connecting you to the night sky. This is a program that we are bringing you live through Facebook as part of our Franklin Institute at Home program. This program actually is replacing our Night Skies at the Observatory program, which we've done at Franklin Institute for many years. That program is a monthly program in which we invite you to come visit us at the Franklin Institute, where we pull together all of our astronomical resources, our observatory, our fourth floor observatory, our planetarium, and our fifth floor rooftop deck observatory, where we add additional telescopes along with all sorts of activities and programs, all geared to connect you to astronomy right where you live. Now, we haven't been doing that program at the Franklin Institute since COVID-19. We hope to reinstitute that program at the Institute soon. And when we get back to that, we'll be sure to let you know, because we'd love to have you come down and join us. But in the meantime, we're doing this program for you here on Facebook so that you can join us at home. The idea being that you can actually discover astronomy right where you live. Astronomy isn't the thing that you find only at the big building downtown or at that special location way up in the mountains someplace. It's something that you can do right from where you live. And it doesn't matter if you're in an urban environment or if you're in a rural or suburban environment, you can still see plenty in the night sky. Now, many people often want to argue that if you live in an urban area, the night lights of the city are so bright that you can't really see very much of the night sky. And I have to admit, yes, there are some limitations, but that by no means means that you can't see anything. In fact, what happens is under an urban sky, you have sort of an advantage, actually, because those extra lights from the buildings and the street lights and things like that actually take out a lot of the dimmer background stars and leave us with just the brightest stars of the prominent constellations. So it makes it easier for you to identify those constellations. But you can also see all of the brightest planets of the solar system and even a number of significant spacecraft. So this means there's plenty for you to see in an urban environment if you just go outside and take a few moments to look around. So if you're looking from your backyard, if you're looking from your front porch, if you're looking from your front steps, any of those environments will show you plenty of the night sky that you can get hooked into. And we're giving you and asking you, inviting you to join us on this little adventure this evening as we help you understand more about the sky right above your heads. So welcome to our program tonight, Night Skies at Home, the Franklin Institute's astronomy program that we bring every month. This is the June 2022 edition of that program, our 35th in this series, and we're glad to have you aboard with us this evening. So tonight we have a lot of really great stuff that we're going to do on our program. Of course, we're going to take a look at a map of the night sky and see what constellations and planets are available for you to see at what time. We'll talk about what other astronomical phenomenon are happening this month that you might want to pay attention to, things like moon phases. And as it turns out, there's a very interesting thing happening this month that has to do with the Earth's position in its orbit around the sun. That's going to be very cool for us to recognize when we get to that point. And we'll talk about exactly when that's going to happen during our program today. So as I said, we'll do what's up in the night sky for you to see. And we'll also take your questions about astronomy. We love to get your questions. So please think of astronomy questions that might be related to our program this evening. And also our special guest this evening is Dr. Aileen O'Donoghue, the Henry Priest Professor of Physics at St. Lawrence University. And we're going to talk with her about radio astronomy, and in particular, we're also going to talk about the Event Horizon Telescope's discovery, or shall I say, imaging of a supermassive black hole right here in the core of our galaxy. If you heard some about this last month, Well, here's your opportunity to learn even more about it, and we can ask some questions about black holes and about the supermassive black hole as well. That's right at the core of our galaxy, as imaged by the Event Horizon Telescope. Dr. O'Donoghue is going to work with us tonight to help us understand some of that. Also, let us know where you're listening from. We'd love to know where you're observing the night sky, whether you're in a city someplace or if you're way out in the country in the boonies. As it turns out, I am broadcasting this program tonight. We'd love to find out where you are. So please let us know. Let us know where you are. We'd love to find out where you're observing from. Okay, great. Fabulous. So let's get started with a little bit of the sky phenomenon that you need to know for this month. Remember, we said we talk about what's up in the night sky. Well, let's just do some of the sky phenomena that you actually need to know. Sunrise now. Sunrise now in the Philadelphia area is coming at 5:33 a.m. 5:30 in the morning. That's when the sun is just peaking above the eastern horizon, and sunset now comes at 8:23 p.m. That's very late, but we'll still get a few more minutes added to the day on the sunset portion of the day and a little bit in the pre-dawn portion as well. So we're going to add still another few minutes onto the day. Right now we are at 14 hours, 55 minutes, I think it is, for the amount of sunlight that we're receiving during the day right now. So we're going to add to that. The days are, quote unquote, going to get longer. We're going to have more sunlight in our days, actually. And that's going to take us right up until the middle portion of the month. We'll talk about that in just a moment. And then the other phenomenon begins to happen. We'll get to that. Just hold on for a minute before we get to that. We'll get there. So there's that. So the moon right now, the moon is a waxing crescent. It's a waxing crescent. It's just 3 days old. That means the moon is visible in the western sky just after sunset. Now, 3 days old means it's not far above the western horizon at sunset. And over the next several days, the moon will climb successively higher in the sky every night. And you can even see that thin crescent as it appears right now. It's very much like what you might call a banana or fingernail moon, just a very thin crescent over in the western sky after sunset. If you have clear skies where you are, you're going to see that tonight after sunset. And if it's not clear where you are, hopefully tomorrow night or the following night, the skies will clear up and you'll be able to see it. The moon will come to its first quarter position in the sky, its first quarter phase in about 5 days, June 6th, June 7th, it'll be at first quarter. You'll be able to see that it looks like a half moon in the sky. And if you think about it just a little bit about how the moon can be in that location or have the appearance that it has at that time, let's go back to your geology lessons and geology classes from junior high school and high school. And we're going to talk about 90-degree angles. It's that portion of the moon's motion around the Earth when it gets to just a 90-degree angle position relative to the sun through the Earth at the vertex that we can see the moon as a half moon or this first quarter. So just think about that. When you're out observing on July 6th, on June 6th or June 7th, you're standing right at the vertex of that 90-degree angle between the moon and the sun. And you can continue to watch the moon as it makes its way towards full, which will come up on June 14th. I think that's Flag Day. Is that right? June 14th is Flag Day. So on Flag Day, the moon will be at full, its full phase. And that's when it's actually directly opposite the sun in the sky. On that date, the moon rises as the sun sets and sets as the sun rises. So that's a great time to get up and observe the moon. Better yet, if you want to get a really good view, especially if you have a telescope and you want to give that telescope a little bit of a workout for its spring and late spring and early summer season, try getting a look at the moon while it's near its first quarter phases. That will give you the best observing of the moon, actually, because that angle allows for shadows to be created by the crater rims and the mountains on the moon. And that shadowing helps to provide the three-dimensional view that lets you see how deep the craters are and how tall the mountains are on the surface of the moon. So that's a good time to do that. Full moon, not such a great time. The moon is too bright, really, to observe through a telescope. So try it on first quarter. You'll see what I mean, and you'll really enjoy it. Okay, so coming up, I was going to mention this. Summer solstice is coming up soon. June 21st this year at 5:13 in the morning, 5:13 a.m. is when the Earth reaches this really interesting position in its orbit around the sun, where the northern portion of the Earth has its greatest tilt toward the sun. And because of that, we have the greatest number of hours of daylight on the northern portion of the planet. And this is our summertime, when the northern portion of the planet gets its greatest heating during the course of the year. For the other half of the planet, it's the opposite season. It's the opposite season down south, and they're just getting towards their first day of winter. So for us, first day of summer coming up on June 21st at 5:13 in the morning. You can't miss it. You're on the planet, you're riding along, but it's actually just an instant in time, because this moment of summer solstice marks the point in the Earth's motion around the sun when it reaches this particular position. Well, once it gets there, it's not as if the Earth actually stops at that location. No, it continues on. So it's actually an instant in time that we can identify as the summer solstice, when the top of the Earth, the northern portion of the Earth, is tilted towards the sun. So here we are coming up on it in just a couple of weeks, summer solstice. And there's one other thing about that summer solstice piece that's actually sort of counterintuitive. I'll give you a little bit of a hint. It has to do with the Earth's proximity to the sun. So here's the hint. I said it's counterintuitive. You would think if the Earth is really warm, the northern portion of the Earth is really warm, that means that the Earth is nearing its closest point to the sun for the year. But remember, I said it's counterintuitive. So there's a hint as to what's really going on. It's an odd I shouldn't say it's an odd thing. It's not odd. It's totally natural, in fact, that the Earth has this relationship to the sun. So keep that in mind. Maybe you'll figure it out. Let's give a shout out to our listeners who are listening to us from all across the place. Oh, we have folks from Rensselaer Falls, New York. Rensselaer Falls, New York. I wonder if those folks are on Putney Road in Rensselaer Falls, New York. I don't know. How about folks in Wynwood, Pennsylvania, Charlotte, North Carolina, Scott Township, Pennsylvania, in Connecticut, in Philadelphia, in Cochranville, Pennsylvania, in Linwood, Washington. Hey, way out there on the West Coast in Linwood, Washington. Thank you very much for joining us. Little Falls, New Jersey as well, and also Queens, New York. Great to hear you from Queens, New York. So thanks everybody for joining us tonight. If you're listening and you haven't let us know where you're listening to us from, please let us know. We'd love to find out where you're enjoying this program from. Now, as we talk about the night sky in this program, guess what? No matter where you are across the country, the night sky as we describe it will work well for you. The locations of the constellations, the time at which you're observing, you may adjust to where you are in the country. After all, you're not going to see constellations during the day in California when it's already dark on the East Coast. But you get the point. It's not going to be very much difference. The only time we really have radical differences in what's available in the sky is whether you're either north or south of the location that where we're describing from. So if you're here in the United States, everything's good for you. If you happen to be in Tierra del Fuego, down at the tip of South America, you probably have a slightly different sky. But what we describe here is certainly good all the way down through Florida, and you'll pick up a little bit of additional stuff in the southern sky and maybe lose a little bit in the northern sky. But generally speaking, for the constellations we're talking about tonight, you'll be in good shape. Okay, so that's the beginning of everything we're gonna, some of the stuff that's available in the night sky. We'll talk about the exiting spring constellations and entering summer constellations a little bit later when we bring up a star map, and we'll have a chance to go into that in detail. And we'll also talk about what space stations are available for you to see in orbit around the planet as you're out under the night sky. And there are a couple of interesting launches coming up in the next few days as well that you might want to keep track of, probably online. But right now, let's do this. It's time for us to bring in our guest astronomer for this evening. And I am very, very pleased to bring to you Dr. Aileen O'Donoghue, the Henry Priest professor of physics at St. Lawrence University in Canton, New York. St. Lawrence University is my alma mater. I'm very proud to be a graduate of St. Lawrence University. I'm also on the board of trustees, and it's a great place to view the night sky because the skies can be very clear and very dark here. And I'm actually on vacation here enjoying the night skies when the sky is clear. And I've asked Dr. O'Donoghue to join us so we can chat a little bit this evening about radio astronomy. And I've asked her because I know that she does radio astronomy work. I've actually sat in on some observing sessions with her, and that was great fun. But tonight we're going to talk a little bit more in detail about the work that she's doing, about radio astronomy in general, and we're going to talk about the supermassive black hole found at the core of our galaxy, our Milky Way galaxy, that was imaged by a telescope called the Event Horizon Telescope that allows us to get an idea of what some of these objects look like. So I'm going to ask Dr. O'Donoghue to join us right now. Eileen, if you're there, please join us, and let's get talking about radio astronomy. Hey, how are you?
Hey, you're right. Hey, how you doing, Derek? It's good to see you.
Good to see you too.
And we're proud of having you have graduated from St. Lawrence too.
Well, thank you. Thank you. I'm so glad you could join us this evening. You know, we, whenever I'm in Canton, New York, we get together and we get to talk about astronomy and the work that you're doing and what's going on in the world in general. But I thought this would be a really, really wonderful opportunity to share with the rest of our audience the kind of work that you're doing at St. Lawrence, and also to talk a little bit about the research that you're doing, and to just have a great time chatting with you about radio astronomy and about the Event Horizon Telescope and that great image that was created recently.
Amazing image. Yes, yes.
Isn't that unbelievable? So tell us, let's start out first. Why don't you tell us exactly all you do at St. Lawrence University, and don't forget the part about the hat too, please, if you will.
Primarily, I teach classes at St. Lawrence University. I'm a physics professor, so I teach a physics class, usually a sophomore or a junior level class in physics. And then I teach astronomy, and I also teach a class called Global Climate, where I explore meteorology and climate issues. As well as doing those, I also do research. I am a radio astronomer. I learned how to do research at the Very Large Array Radio Telescope outside of Socorro, New Mexico, where I did my graduate work. And since moving to the East on a fling to teach at a private liberal arts college, which I could never have gotten into or paid for.
You snuck in the back door as a professor, right?
I did. And so I continued my research using the Arecibo radio telescope, which unfortunately met a terrible demise in December of 2020. And so now converting over to using the Green Bank telescope in Green Bank, West Virginia. And actually we have an observing program going on now. We get assigned, here you can use the telescope for 4 hours. And wherever we are, we get on the computer and we use that telescope in West Virginia because it doesn't know where the computer is that you're typing on. It's, and it just obeys the commands. And in my work, I look at galaxies, but I don't look at black holes in the centers of galaxies. I used to look, when I started my career, I looked at the stuff these black holes squirted out a long way from the center of the galaxy. But now I look at the hydrogen atoms that mostly hang out in the plane of the galaxy. And our work is to find these, mostly we look at small kind of dwarfish galaxies, not the big, huge, pretty ones that you see on, the Hubble site, but these little blue smudges in the night sky. And what we do is that we try to figure out where they are and how they're moving, because the universe is, of course, expanding. It's been expanding for 13.8 billion years now. And it's not that the universe is stuff expanding into pre-existing space. It's all of the matter and energy that was in a volume smaller than the proton of an atom, it all blew out. And it's not empty. There's this stuff called dark matter, and it's this web and these tendrils. It almost looks like a neural network if you look at the dark matter pattern. And in our local neighborhood, we're looking at how galaxies move and where they are to see if we can figure out the distribution of the dark matter, because the only way dark matter talks to us is through its gravitational pull. And so galaxies are falling toward dark matter. And so that's the work that I do, and that I have students working with me. I'm taking 3 of them to Green Bank in a couple of weeks. So that's what I do. And then, being a faculty member, there's teaching and the research. And then the third job is being a member of the university. And so we have committees we serve on and things like that. And I happen to be the university marshal, which I absolutely love. And one of my professors in graduate school actually gave me a poster of Mickey Mouse as the sorcerer's apprentice. And he signed it, wishing me well in my career. And I actually, in Silver City, New Mexico, actually found a felt hat that is, it's a cone, it's a pointed hat, and it's purple, dark purple with gold stars on it. And of course, a wizard's hat has no brim. A witch's hat has a solid brim. Mine has a jagged brim, so it's a little bit of both.
Yeah, I've seen this hat, and it is fantastic.
So I get to lead the parade, of course, with academic tassels on it,
Oh, of course, certainly.
My full regalia, with all the frou-frou. So I
The
have
robe and the stole and everything with the hat.
And the medal, and yes. It's a lot of fun. And
It's a lot of fun.
Always happy to see you show up for commencement. So,
Well, part of the reason why I come for commencement is so I can see you in this great hat. It's fantastic. It's a great way to lead a commencement. It really is. But so let's get back to the work that you do in radio astronomy, Aileen. We often throw these words around quite liberally without very much explanation. As when we're talking as colleagues, we sort of get it. But, on the other hand, it's often difficult to talk about the other wavelengths of light that astronomers use to observe through. And while, it's very easy for people to get a hold of visible light telescopes and understand how they work, it's more difficult to understand the others. So, radio astronomy is a really big piece of astronomy, but the instrumentation it uses is different. So let's talk a bit about how do radio telescopes work? What is it that you are detecting, and what do you see when you point a radio telescope towards an object?
Essentially, I see what you see if you have an analog radio. Little transistor radio, or a fancy one, not a digital, but one that picks up the radio waves from your local radio station. And so it's those waves from the radio station to your radio. Those kinds of waves are what we detect. And we detect them with antennas and receivers, much like the antennas and receivers in your little radio. And so they are a bigger wave than optical waves. They're lower energy and a lower frequency and a much longer wave. The waves that I usually am looking at are about 21 centimeters in wavelength. Now, an optical wave is about 600 nanometers.
A little smaller.
Yeah, it's 10 to the minus 9. And so radio waves are much bigger. They're 10 million times bigger than optical waves. So we need bigger instruments. And that's what we detect. And so the nice thing about radio, it's like, your transistor radio works even if it's foggy. Even if you can't see the radio station, the radio waves get through. And not always from the satellites, because there's this pesky thing called the ionosphere that screws things up. But
Ah,
from
okay.
the radio station to your radio, those go through fog. And so with radio astronomy, we can see through the signals from objects that are hidden behind dust come through to us. Whereas with the optical telescope people that use those, the fancy telescopes on, Mount Palomar and Kitt Peak and Mauna Kea in Hawaii and down in Chile, clouds block them out. They can't see it. Clouds of dust in the spiral arms of the Milky Way block them out. And so when we go to look to the center of the Milky Way, we need to use radio because the dust doesn't block it. And we have a very dusty galaxy.
So wait, so this means that with radio telescopes, you can actually see through the dust. You can penetrate the dust, and whatever objects are generating that energy behind this sort of curtain or this veil of dust, you can actually detect radiation coming from those objects through that cloud that other telescopes can't see through.
Yes, and there are other wavelengths, some of the ultraviolet and some of the infrared X-rays, they also get through stuff that optical, we just can't see through it. So it's, and also we see different processes going on. The stuff that emits visible light, the processes that emit visible light, they also emit radio and X-ray and infrared, but a lot of them. But there are a lot of processes that don't emit in visible, that do emit in radio frequencies or do emit in ultraviolet frequencies. And so if we want to see all of the objects in the universe, we need to look at different wavelengths of the electromagnetic spectrum, is what it's called, from gamma rays and X-rays and ultraviolet and visible, infrared and radio. And they each give us a different view. It's like looking at the universe through different colored lenses.
Oh, yeah, very cool. That sounds great.
That's what we do.
So radio provides yet another type of information to add to the other information that can then be put together to make a much more complete picture or understanding of what kind of process might be taking place at some astronomical object that you're observing.
Right. So, for instance, in radio, we see the plane of the Milky Way galaxy that's mostly hydrogen, cool hydrogen gas, all right, not cold. Cold is H2, where you have two atoms bound to each other. Hot hydrogen gas, it loses its electrons, so it's ions. But cool gas is just hydrogen atoms, and they glow at 21 centimeters. And so we can look at those. And also in the Milky Way, some things my group has observed is that between us and other galaxies we're looking at, we'll find a little blip of hydrogen. And they turn out to be clouds of hydrogen gas that have been blown out of our galaxy by things like supernovas.
Wow.
And so there are these clouds of gas that get blown up, they come falling back in. And so it turns out the around the Milky Way galaxy, there's all this action going on. There's clouds bursting out, falling back. And so we see clouds of hydrogen. In optical, you're not going to see a cloud of hydrogen because it's invisible.
Got it.
Seeing the oxygen in the air between us. We just can't see it.
Oh, very cool. Very cool. So that turns out that the universe can show its dynamic nature in some of these other wavelengths like radio that you might not be able to see invisible. Yes. And that again helps to fill in another part of the story of what's going on out there.
Yes. And like your radio, when you turn into a radio station, you turn to a certain frequency. All right. 84.5 megahertz for North Country Public Radio. And 89.
That was sneaky.
80, I can't remember. I don't tune them anymore. They're digital. But turn it. And so when we look in radio, we don't make pictures the way you take pictures in optical. We look at the spectrum. We look at what energy are we getting in each channel at each frequency. It's like mapping the radio dial with, oh, there's a station moving along. Oh, there's a station. And each one of those stations is a different cloud of hydrogen. And they're moving at different velocities. And so when we look in radio, we get how fast things are moving toward us, or away from us. And so that's also different information than you can get in the optical. You can get some of that in optical as well. So it's different information as well as different objects.
Is learning how to interpret this in any way similar to learning a new language?
Oh, it's a lot easier. Much easier. They're looking at squiggles. It's like, oh, it's right there. Yes. Having tried to learn Spanish in New Mexico, no, this is much easier. But you know, every specialty, every endeavor. I mean, HVAC people, right? Heating, ventilation, air conditioning. They have their own different language. You know, every trade has its different languages, and this is the astronomy trade. And so, yeah, we do learn a different language, and some of it requires learning math and using math, but math is really just a shortcut explaining relationships among things.
Well, I think I just want to highlight that one point that you brought out for all of those listening who were sort of trying to decide if they were going to go linguistics or astrophysics. You just cleared it up that they should definitely go the easier way, the astrophysics way.
Well, that's what I thought, you know.
Well, that's great. I think that helps, that people can better understand this a little bit by thinking of it as learning a different language to understand how to interpret what the radio signals are like. So let's talk a little bit now, Aileen, about instrumentation, because you mentioned the Arecibo Radio Telescope, which is a very big radio telescope in Puerto Rico that you've worked with. You now have talked about working with the Green Bank Radio Observatory in Green Bank, West Virginia. And then in the story that broke in early May about a supermassive black hole at the core of our galaxy, our Milky Way, our audiences heard about an Event Horizon Telescope. And, you know, I think, you know, perhaps people have gotten an idea about the Event Horizon Telescope as being a telescope that can look at the event horizon of black holes, but it's a little bit more. It's a little bit more than that. So let's start back with the instrumentation you have used. You said that you worked with the VLA, the Very Large Array, and then you went on to the Arecibo Telescope. Tell us a little bit about those instruments. You also said they're big. So what are we talking about, big?
So let's talk about Arecibo. So Arecibo, it was a spherical reflector. Now, radio waves are big. So 1/4-inch hardware cloth, you know, which is a woven aluminum with 1/4-inch holes, that looks shiny to radio waves. They bounce off of that. They don't know there are holes.
Oh,
and so
wow.
It was this big reflective dish. It was 1,000 feet across, 300 meters, 305 meters across.
1,000 feet across.
Dish. And we had a detector up above it that basically we couldn't steer the telescope because it was hanging in a valley 1,000 feet across.
Okay.
So what we did is instead, so we have our dish here, we'd move our head around and look at the reflection of the sky on the dish.
Okay.
All right.
All right.
And so
cool.
That initially that had a line, what they call a line feed antenna, like the antenna you pull out of your transistor radio. Very similar. But then we developed more sophisticated receivers, the receiver that's actually in the radio, not the antenna. And so then we could use a different instrument. But it was about the simplest radio telescope. And it was basically a 1-pixel camera. When you observed, it was just bright. How bright is it? And you had to put together all the observations to create a map by scanning, looking around at the different places in the object and creating an image over time. So it took a lot of work to do that. And at Green Bank, we have the antenna at Green Bank can move. So it can look around at the sky.
So you can point that around to
Yeah, we
different
can
places in the
point it.
sky.
And it's that one is 100 meters across.
100 meters.
Yeah, so
Okay.
you can think of it as a football field across. The whole surface of the dish is 2 acres.
Yes.
So we've got 2 acres of curved dish that we can move around. And now the receivers are more sophisticated, so it's not as hard to build an image. The very large array where I started, now that's more like the Event Horizon Telescope, because what we wanted to do, you have bigger waves, you need a bigger instrument. If we wanted to see the same level of detail, okay, the resolution, like your resolution is at what distance can you separate the 2 headlights of a car, right? Far away, it's 1 light. And then as they come forward toward you, you can see 2. And so your resolution is how, how well you can see 2 headlights instead of 1. We wanted to match the ability of the Palomar 5-meter or 200-inch telescope with radio. Turns out we needed a radio telescope 35 kilometers in diameter, which is an engineering problem.
Yes.
So instead, they broke it into 27 pieces and laid it out on the ground and used the computer to look at what each antenna sees and put it together as though it was one telescope.
So wait, instead of having one single telescope 35 kilometers across, you're now describing 27 different antennas spread out across that 35 kilometers, and then using computers, pulling together the signals from each one of those to simulate a single instrument 35 kilometers across.
Right. And they're shaped in a Y. All right. I can't really do a Y with my fingers. They're shaped in a Y. And as the Earth turns, the Y turns. And so as you observe an object over time, the telescope kind of fills in.
Ah, okay.
And it's called Earth rotation aperture synthesis, if you want.
Got it. Earth rotation aperture synthesis.
Word.
Very cool.
Yes.
Okay, now
word for the day. And so that's how we created images with that. The event horizons, and if I could share my screen, I can show an image of it.
Please do. Let's see that.
So let's see. Here it is. Can you see it?
Yes.
Okay. It's a telescope the size of the Earth. And so here, this is showing there's an antenna in Greenland, or excuse me, in Antarctica at the South Pole Telescope. There's some in Chile in here. Here's one out in Hawaii. Here's one in Mexico and in Arizona. This VLBA antenna is in, I think it's in Ohio, the GBT, the Green Bank Telescope in West Virginia. And then we have Max Planck Institute in Germany. And then there's one in Spain. And there's another one, I can't remember if this is in also in Spain. And so we have all these antennas, and like the VLA, as the Earth turns, they fill in the data. And so if I go to a different slide here, we need the bigger waves, need bigger detectors. Think about being in a boat. If you're in a boat, a rowboat, the little choppy waves, you don't even notice. If you're out in the ocean, the big tidal swells, you don't know.
Yes.
But once you notice, they're about the size of your boat. All right. So a bigger boat is, when you're in a rowboat, little 6-foot waves are going to drive you nuts. An aircraft carrier does not notice 6-foot waves.
Right.
All right. And so the radio needs bigger telescopes. And so the optical telescopes, those fantastic images that we see from the Hubble Space Telescope, that's only 8 meters in diameter.
Not very
James
big.
Webb is like 25 meters or something.
Mhm.
All right. But in radio, the Green Bank Telescope is 100 meters in diameter, and the Event Horizons Telescope uses the Earth, the diameter of the Earth, to create these images.
Wow. So
These are
rather
great.
than
Yeah.
right, so rather than trying to build an instrument that's the size of the planet, these individual telescopes placed around the world, again tied together by computers, can synthesize an image with the resolution of a telescope the size of the Earth.
Right. Now, the hard part is that at the Very Large Array, all these antennas were connected to each other with waveguides, which are a different kind of wire. Well,
Mm.
the Event Horizon Telescope, they can't send this data over the web because it's too much data, and it would just overwhelm the internet.
Mhm.
And so instead, one of the hard parts about the Event Horizon Telescope, they all have to be synchronized. They have to all know exactly what minute it is, Greenwich Mean Time or Universal Time, whichever you want to
Mhm.
call it. So
Mhm.
they what they do is that they receive the signals up here in the top.
Mhm.
They convert those to digital signals, waves.
Aha, okay,
This is
yes.
a voltage. Essentially, what the antenna receives is a fluctuating voltage.
Aha, okay. Mhm.
That's what your
Not e-
antenna receives, a
Not
fluctuating
exactly a picture, not
No.
exactly a picture, but a
And so-
fluctuating voltage.
Right.
Okay.
And so you turn that into a digital signal of zeros and
Mhm.
ones.
Mhm.
And and then you have atomic clocks that match the times. Then you write
Mhm.
all these data onto a hard drive. And it is so much data that they then take the hard drives and they get on commercial jets and fly them to MIT and the Max Planck Institute for analysis. They can't send it over the web. And since this is, just these few telescopes, just these
Mhm.
few receivers, so widely dispersed, they're missing a lot of data. And so it's kind of like looking at something outside through a really shattered window.
Aha, okay.
And you've got to somehow construct the image of what's outside by figuring out the shatter of the window. All right.
Ah,
So
okay.
one of the
Mhm.
things you could do is go outside the window with a single bright light and look at it and say, okay, for a single bright light here, this is the image I get. And so
Mhm.
you choose the brightest point on your image, and then you say, okay, I'm going to believe that point. And then you take the whole pattern of the shattered window and throw it away. And then you pick the next bright point. And this is called
Ah,
cleaning the image. Now, that's a very simplistic way to explain it, but that's why it takes these months. These observations went on, I think, in 2017 or 2018.
well, that's a really interesting part about this, Eileen, because I think many people around the world assume that, the Event Horizon Telescope looks at some location in the sky under high magnification, takes a snapshot, and then a Polaroid picture comes out. But this is a process that has taken years to actually put all this together.
Imagine just getting all the airplanes to this, getting all the data in this world,
Right.
all right.
Oh,
that
wait, my
takes
flight
years.
was canceled. Just a second,
But-
they lost my luggage.
But then, with the Very Large Array, with these antennas in the same place relative to each other, we got really good at figuring out the image. But this, it's much harder. And that's why these images are so different
Okay.
from what we've seen before.
Do you have a picture of what
I
it looks like?
Do you want to see where it is in the sky in Philadelphia tonight?
Yeah, let's see where it is. Where is it?
Alright. So here, this is the view from Philadelphia at 2 a.m. You're looking south. And so here, this isn't from Philly. It's a simulation, but there's the constellation of Scorpius. Can you see it now?
Sure. Mhm.
Yes.
Yes,
And
yes.
this is a
Mhm.
bright red star, Antares, the
Antares,
rival
right.
of Mars. arrival
Right.
of
We
Aries.
talk about that quite
And
frequently.
then we have over here, you can kind of pick out a teapot shape. That's
Mhm.
Sagittarius. This is the teapot. This is the teaspoon. Can't have a proper
Aha.
cup of tea without. All right. And
Yes,
so
yes.
then notice this blurry stuff. Can you guys see this okay?
Yes, we can see
Oh,
that
this-
Milky Way right
that's
there.
the Milky Way. And look at
Mhm.
this cute little thing. If you make a little triangle, diamond out of the spout of the teapot, you see that thing. That's called the Lagoon Nebula. It's where
Right.
stars are being born. They're forming right now as we speak.
Mhm.
And then, surprisingly, you talked about the summer solstice. Well, this is at 2 in the morning. And so there is the winter solstice on the
Ah,
opposite
okay.
side of the sky.
Right.
Cool. Yes,
Mhm.
right by the lagoon. There's the equator of our galaxy. And so
Right.
this thing right in here, that is the galactic center. So you can go and look at it from Philadelphia tonight.
Very cool. So between those two constellations, right there in the middle,
Right
we
there in
could
the
actually
middle,
go
you
out
know,
and look
the
in that
spout
direction
kinda-
towards where this
and-
is.
Yeah, here's the spout, here's the spout. So it's kind of between these two lines. Can you see my cursor?
Yes.
Okay,
Got it.
so- yeah, so that's
Excellent.
where it is. And so this is Green Bank Telescope back here. I've just kind of
Mhm.
graded out for the so you can see the text.
Mhm.
But the way we started focusing in on where this thing was that we were looking at stars. So this is 1995 June. I'm going to play this, watch this number, and this is observations over years of these different stars. And watch how they move. And there's obviously something where that little star is that they're orbiting. And when
Oh,
they
I see.
go
We
whipping
can look
around.
at how the stars loop around the
Yes,
object in the center.
right. And we can look at all those orbits. And these are actual stars. And this took
10.
place 30,000 years ago.
20 years. Wow.
Yeah. So now here we
So-
are in 2020.
Mhm.
And this is one of the stars.
Got it.
All right. And
Mhm.
so this is the area, and that some of these are those stars. And right in there is Sagittarius A star. That is where the black hole is.
Very cool. Now, if we go outside and look in that direction, we can't expect that we're actually going to see anything.
No, you're going to see stars.
But radio telescopes allow us to see more in that direction,
Right,
as you
right, because-
demonstrated.
Yeah, this is all hidden from optical telescopes by dust and different gas clouds. But the radio waves from these different stars, and these are at 6 centimeter radio waves, a lot of them.
Mhm.
And so those radio waves can penetrate through that dust, and they get dimmed a little bit, but they get through.
Okay. All right. So now
Right.
we conclude. Now we really can understand how radio telescopes help us to see these things. That's
Yes,
cool.
yes,
Okay. So here's a view of what the radio information
This
has
is-
detected.
This is it. And it's like, yeah, they figured out from the mass. I mean, Newton told us if you can see how fast something is orbiting something else, you can write down from Newton's laws what the mass of the thing it's orbiting is.
Mhm.
Very old
Cool.
science. And so we figured out the mass. And the mass is 4.3 times the mass of the sun. M sub sun is the mass of the sun. The event horizon, the sphere in which light is trapped,
Mhm.
is 16 million miles across.
So that's this like orange donut that we're seeing.
That's the inside. That's where it's dark.
The inside is 16
that's
million
the
light
event
years
horizon.
across, 16 million miles across.
This donut is what we're seeing is an image. The stuff is falling into the black hole. And anytime stuff falls in, it tends to establish a plane where it orbits into the black hole. And so what we're seeing is the stuff falling into the black hole, and it's going really fast.
Mhm.
And so, yeah. And so the event horizon is 16 million miles. The distance from the Earth to the sun is 93 million miles. So this is a tiny thing, but it's
Yeah.
got 4.3 million times the mass of the sun in there. Actually, the radius of the stuff is down to 0. Of course, only God can divide by 0, which is why God can make black holes and we can't.
And so that explains, because of the incredible mass here, that explains why the gravitational pull is so high and
Yeah.
why light and other radiations can't escape from
It's
black
a
holes.
huge mass with no radius. All right.
Well,
Remember,
okay.
we're falling toward the center of the Earth. And fortunately, we have a surface that stops us from falling in.
Right.
If you crammed all of the mass of the Earth into a cubic millimeter, then we would just keep falling. And the gravity would get very strong. All right.
Yes. Yes.
So,
Mm-hmm.
yeah.
Right. But we'd
And
have to be
that's the
down to
thing.
that tiny size.
Yeah. Yes. Yes.
Mhm.
And so the outside of this donut is about 72 million miles, which is Mercury's orbit. And on the
Wow.
sky, it's only 8 nano degrees. Your
Wow.
pinky finger, hold your pinky finger at arm's length. I can't get far
Mhm.
away. And it's about a degree
Mm-hmm.
held out. All right. So that is for your pinky finger, it's 0.00003. It's 300 thousandths of the width of your pinky finger at arm's length. It's tiny. This is why it took a telescope the size of the Earth to see it.
Back to the
It's
resolution again.
Tiny. Back to resolution.
Yes. At
Or
that
you
distance.
can also say, yeah, it's the size of a donut on the surface of the moon.
There we go. That's
Yeah.
great.
It'd be
Wow.
stale. I wouldn't eat that.
It wouldn't
I
be
mean,
good for your teeth, that's
5-second
for
rule
sure.
or not, you know?
Right, 5-second rule or not. Well,
Yeah.
this is an incredible explanation of what it is astronomers are talking about, why astronomers are so excited about this, and how this image comes to be. Given that we need radio telescopes of this enormous size to get this kind of resolution, and that I think one of the other things I learned about this, Eileen, is it takes thousands and thousands and thousands of images or data. How do I say data points? Not data points, but essentially thousands of images to create what we now see as an average, really, of those thousands or even hundreds of thousands of images to give us what we see of this. I think one of the most surprising things, again, is that it has taken years to pull this data together and to check it all out to make sure it's good.
Right. And it takes, it's tremendous. Without computers, we wouldn't be able to do it.
Yeah,
And
without computers, we
remember,
wouldn't be able to do it.
We're not looking at the black hole.
Right.
Light gets out of the black
Mhm.
hole. The black hole absorbs light from all around it. So what we see is the shadow of the black hole and the disk of material that's falling into the black hole. But the black hole's gravity is so strong, it warps space and it bends light. And it's really not very bright. This thing is only about 100 times brighter than the sun, but it's like 27,000 light years away from us. So it's really, really dim, which means we had to observe it for a long, long time. A real long exposure image. So they're observing this for days.
Wow. And with a telescope the size of the Earth.
Yeah. And each one of them in a different time zone.
So Eileen, we have to let this be the last image.
Okay, but this explains kind of what we see. So what this shows is here's the disk of material falling in. This is the image of the far side of the disk, and the light is going out, but it gets bent toward us. This down here at the bottom, that's the underside of the disk on the other side, and it gets bent coming at us. That's why we see these images. And the bright spot, because this is stuff in the disk coming right at us, and like a lighthouse, it beams its radiation in the direction it's going. and they're clumpy things. So these other two, these are knots of material. But here's the one from M87. Notice the size. This one is
Oh,
Mercury's
yes.
orbit. Here's Pluto's orbit inside
Yeah.
the shadow of the black hole.
Right. So Sagittarius A star is very much smaller than M87 was.
Yes,
Yeah, very
M87
much
is
smaller.
1,000 times bigger, but it was 1,000 times farther away.
And just to remind our audience, the M87 image was the first of the black hole images that was created by the Event Horizon Telescope. Eileen, I think we have a question for you.
Hey, that'd be great.
Nate,
Let's see what it is. The question comes from Nate. What is it, hon?
I'd like to know, is there a sound from a black hole? And if so, how does it emanate? Can you explain?
Eileen, the question is essentially, do black holes make noise? Do black holes make sounds? And if they do, how do they emanate? How might they emanate a sound?
So, Nate,
Yeah, well,
Thanks, Nate.
there are a lot of material colliding and falling in. I'm sure they make sound. The problem is they make vibrations when the particles run into each other. The problem is there's no air, there's no medium to carry that. The light can weave itself through empty space. Sound needs a medium, it needs the air. So no, we couldn't hear the black holes. But I'm sure there's so much turbulence. I'm sure there's a lot of noise. If you put one in an atmosphere, though, it'd really blow up.
I was going to say, Eileen, yeah, I guess we could get a black hole to make a sound that we could hear if we could get it in an atmosphere that had a medium like air, but then we'd have a whole other set of things going on about having a black hole in an environment with air. Yeah,
my
that'd be tough.
introductory physics students claim that a flux of black holes flies through the lab when they're trying to measure gravity, and that's why their measurements don't match the standard.
Well, thanks, Nate. Thanks for that question. That was really great. Eileen, that image that you just showed before this one is a really super one. And, I want to thank you for.
Yeah.
If you can throw that up there again. Yeah.
Yeah. Google NASA, diagram black holes.
NASA diagram black hole. Okay.
Yeah, just Google that and you can find this image. And they actually, on their site, they have it animated.
Oh, that's great.
And so you can see how everything is moving. There is just tremendous stuff online. If you just Google Sagittarius A black hole or Event Horizon Telescope, all kinds of explanations. And if you Google image of a black hole explained, you'll get, there's a YouTube video by an astrophysicist, Dr. Becky, and it's a fantastic explanation. I highly recommend her explanations. So there's
Eileen,
great
if you will send me those links, I'll be sure to post those so that our viewers can follow them.
I'm happy to.
Eileen, thank you so very much for taking the time to go through this with us. I mean, I think it's been very, very helpful. And
I don't have to give a quiz.
You don't have to give a quiz, right? And the images are really stunning. And thank you so much for doing this. I'm glad we had a chance to get together and do this. And I think this really has helped our audience to understand a lot better how radio astronomy works, and in particular, how radio astronomy works to create these images for supermassive black holes. So thanks a lot. I hope to see you soon.
Derrick. All right, see you soon.
Sure, and we'll talk again soon. Thanks. Folks, that's Dr. Aileen O'Donoghue, who is the Henry Priest Professor of Physics at St. Lawrence University. She's a radio astronomer who actually is studying galactic motion using radio telescopes, but she was helping us this evening understand a bit more about how radio telescopes work and also understanding how we could create an image of a supermassive black hole at the core of our galaxy, our Milky Way. So we hope you enjoy that. Please send us your questions. We have listeners this evening from Voorhees, New Jersey, from Newtown, Pennsylvania, from Bogota, Colombia. Hello, Bogota, Colombia. Glad to hear you. I've been to Bogota. It's a lovely place and I'd love to come back. Folks in the Poconos, and from Buffalo, New York. Oh, I have to give a shout out, please, to Ann McBride. Hello, Annie. How are you? I'm so glad you have joined us this evening. I owe you a phone call, and I hope to talk to you sometime soon, Annie. Thanks a lot for joining. Really glad to hear you're here. Thanks so much. And Samantha Johnson says hello. I'm saying hello to her. She's saying hello to her two favorite scientists. Thank you, Samantha. And thank you for facilitating this program tonight. You really went out of your way to help us get this online. So a big shout out to Samantha for helping us with this tonight. Thanks a lot. And again, hi, Annie. I'm glad you're here. Great to hear you're here. So thanks a lot, folks, for joining us for this portion of our program. We still have a bunch of stuff we have to do and a few minutes to do it. So let's get on with the rest of what we're doing here, because we want to make sure that when you go out under the night sky, you'll be able to identify all those things you want to see in the night sky as well. You recall, as we were speaking before we started talking with Dr. O'Donoghue, we're talking about what's available to be seen in the evening sky this month. We talked a little bit about the moon. We said that first quarter is coming up, June 6th and 7th. That's a little bit later, just a few days from now. And then we'll have full moon on the 14th of June. Full moon is on the 14th of June. Because the weather's nice and warm, this is a great opportunity for you to begin to follow the phasing of the moon. And since the moon is just 3 days old right now, here's a perfect opportunity again for you to sort of follow how the phasing works. If you go outside and observe the moon at the same time every night for the next couple of weeks, you'll be able to identify how the moon orbits around the Earth day by day. Just keep this in mind. The difference in position of the moon in the sky from one day to the next is the moon's orbit around the Earth in that 24-hour period. That little piece of the moon's orbit over a 24-hour period of one day. So if you go out tonight where you are, sky's clear, you'll see the moon where it is. 24 hours later, the moon will have moved a little bit to the left, and that will be about 1/28th. It's really 1/29th of the moon's motion around the Earth. About 1/29th of the moon's motion around the Earth every day. When you put all of those together, you come up with the full phasing of the moon as it orbits the Earth. And then that might help you understand how we're seeing the phases of the moon as we see them. So that's pretty cool. Get out and do that observation. You'll enjoy that. But you know what? There are also great constellations to be seen in the sky. And what I'm going to do now is I'm going to share my screen here so that we can go up and see if I can get to my sky that I want to get to here. Let's see if I can do this. Oh, look at that. I have to do some really fancy dancing here to allow Zoom to share my screen. I have to open up my preferences and security to grant access. So guess what? We're going to skip that, folks. We're going to let that go. And just a second, we'll skip that. It looks like I'm not going to be able to share my screen just because of some security issue. And I don't want to lose you here. So let's just continue with what we're doing and we'll go from there. So just a moment. Let me see if I have one other way to do this possibly. I'll try that one more time and see if I can get that to work for me. And the answer is no, I can't. Oh, how about that? Well, things happen like this. So let's talk about what's out there for you to see. Now, if you looked at, hey, Aileen, are you still there?
I am.
Aileen, can you do me a favor, please? Can you go back to your slide deck, share your screen, and let's go back to that slide where you showed the constellations of the evening sky for Philadelphia, if you can, please.
Let me just bring it up.
Folks, this is called team teaching on the fly.
Okay. Okay, here's the Philly sky and share screen. Yeah. You're using St. Lawrence security. Fortunately, I've had years. All right, slideshow.
Okay, perfect.
There's the Philly sky.
Thank you. Okay, so two really great constellations for us to see in the summer sky. As Aileen points out, this is 2 o'clock in the morning, looking toward the south. So rather than have you be up at 2 o'clock in the morning, let's just say it this way. If you were observing at about 11 p.m., these constellations would be a little bit over to your left, over toward the eastern portion of the sky a little bit. But these are two really great ones. We have the constellation Scorpius that you see here that looks like a big swirling S shape. And that swirling S shape that you see along there describes the shape of a scorpion. If we go to the right of the bright red star Antares, you'll see a vertical line of stars. And those three stars that are that vertical line mark the head of the scorpion. So Aileen will mark those for us. There's the head of the scorpion right there. Antares, the red star, is actually the heart of the scorpion. And it really is a red star. As Aileen pointed out, this particular star is named Antares because it's supposed to be, the word actually is anti-Mars, Antares. It's two words put together. And it was named that so that people would be able to differentiate between the red star itself and the planet Mars that can also appear in the same portion of the sky. So one would be a planet, one is the star. The Greek name for Mars was Ares. And since this star has that same anti-name, it's Antares, Anti-Ares, which means not Mars. So you have Mars and not Mars. So that's the heart of the scorpion. If we come down along the body of the scorpion and swing around to the tail of the scorpion, right there on the end, there's a pair of stars, the bright one of which is called Shaola. And Shaola means the stinger. So for ancient sky observers, this was seen as a scorpion in the sky with a heart, a tail, and a head. So that takes care of that one. This is bright stars that everyone can see without too much difficulty. Now over to the left, or a little bit to the east, we see the constellation Sagittarius that Aileen pointed out as being shaped like a teapot. And so the bright stars of this constellation easily outline what a teapot shape looks like. So if you can identify where the scorpion is, all you have to do is slide over to your left a little bit as you're observing, and you'll be able to find where the teapot is. Now, the very cool thing about these two constellations is that they're actually split apart or separated by the arms of our galaxy, our Milky Way. And as Aileen pointed out earlier, if you just go off the tip of the spout of the teapot, you'll end up in that region of the galaxy that points to galactic center. And if you had a spacecraft with enough fuel and supplies, if you jumped in your spacecraft and flew in that direction in about, 100,000 miles away, 100,000 light years away, you'd be ending up near the center of our galaxy and maybe somewhere near Sagittarius A star, near that black hole. Don't get too close, by the way. But that's the direction of galactic center. Now, if we go up along that Milky Way, going up toward the top of the sky, we come up to three other very bright constellations that mark the summer sky. And that's Cygnus, Lyra, and Altair, that all have very interesting shapes among themselves. But the three brightest stars of those constellations together make up a summer form that's easy to recognize, and that's the shape of a triangle. So if you take the three brightest stars of those constellations up near the top of the sky, those three stars together make up the summer triangle. And it's Deneb from the constellation Cygnus, it's Vega from the constellation Lyra, and it's Altair from the constellation Aquila the Eagle. So those three stars put together make up the summer triangle. So from the summer triangle coming down along the Milky Way into the southern portion where you have Scorpius and Sagittarius, you not only have these five bright constellations of summer, but you also have the summer Milky Way and the direction out toward the center of our galaxy. And that's quite a bit. Now, if you'd like to find something really familiar like the Big Dipper, not too difficult to do, as you're facing south here looking at Scorpius, the Big Dipper is going to be back up over your right shoulder. So you'd look around toward the northwestern sky. And if you're out at about 10 p.m., you'll be able to see the Big Dipper up toward the northwestern sky with its handle dipping over, pointing down toward the western horizon. So as you're facing south, looking out toward Scorpius, look back over your right shoulder, and you'll be able to see where the Big Dipper of the constellation Ursa Major is located. Thank you very much, Aileen. That was great, greatly appreciated. You can stop sharing now. Thanks for doing that for us. We greatly appreciate it. Thanks very much. Okay, we'll see you around. Okay, so last up, folks, Now that we've given you a little bit of that description of the sky, let me just give you a guide for where you can actually go yourself so that you can identify these constellations using a map that's online. If you've been with us before, you know that one of the online maps I like to use is Stellarium Web Online. And so if you simply go to stellarium-web.org, stellarium-web.org, you'll come up with an online star map of which you can manipulate the time quite easily so that you can set it up for observing at your location and whatever time you'd like to observe. And you'll be able to find these constellations as well without much difficulty at all. And in fact, the legend down at the bottom of the screen allows you to add the lines between the stars, add the constellation artwork and the constellation names as well. So you'll be able to find these without too much trouble. Now, one thing I really have to turn you on to that you cannot miss. Did I say can't miss? I said you can't miss. It's bright planets in the pre-dawn sky. Now, I know it sounds early because sunrise is coming at 5:30 in the morning now, but it really is worth it on a clear morning to be up at, say, 4:30 in the morning, 4:45 at the latest, looking over toward the eastern horizon. And this is really good for folks that have a clear view of the eastern horizon, because right now at 4:45 in the morning, Venus is brilliant on the eastern horizon. And if you just take a diagonal line up to the right from Venus, you'll come across two bright objects very close together, Mars and Jupiter together in the sky right now, very close together. And then a little bit further along on that diagonal up to the right from Venus, coming through Jupiter and Mars, you'll find Saturn. So we have four of the brightest planets of the solar system in a line in the eastern sky in the morning before sunrise. You should get out and take a look for that. Remember, it's Venus down closer to the horizon, Mars and Jupiter a little higher, and then Saturn a little bit higher above that. So don't miss that in the pre-dawn sky. If you go use that map, stellarium-web.org, you can also find that there as well to show you what you want to see. Now, as I mentioned, we have a couple of launches coming up pretty soon that you might want to pay attention to. The Chinese Space Agency is launching 3 astronauts up to their space station, Tiangong, on Saturday. That's going to be Saturday night, 10:30 p.m. Eastern time, and you can follow that online without too much trouble. If you simply search Chinese Space Agency or Chinese astronaut launch to their space station, Tiangong, they'll be there for 6 months, and the for 6 months those two Origin, a new Shep flight coming also on Saturday morning. 6 passengers will take the 10-minute flight from the desert Southwest up to the line of space, up to about 62 miles up, and come back down. The launch window for that flight opens at 9 p.m. Eastern time on Saturday morning. They have no constraints for flights, so we can't tell you exactly when the launch is going to take place. It'll happen when everything is just right, when everything is configured properly and the craft is ready to go. That's when they'll launch, but you can follow that online also at Blue Origin. You can go to Blue Origin and find out more information about that. There aren't very many, there aren't any really International Space Station visible passes right now, because Space Station is shifting from being an evening observation target to being a pre-dawn sky target. So it's going to take about 10 days for things to shift over. So we won't have any visible passes, at least in this part of the world, for a little while. But in a couple of weeks, we'll be back on again with pre-dawn passes. And so that's worth checking out. So don't forget, summer solstice is coming up on June 21st. At 5:13 in the morning. So that'll be our first day of summer. We've had all this great stuff to talk about and see in the evening sky. Summer is the perfect time to be out. We have about a minute and a half left. So Linda, do we have a question that we can ask? No questions. Great. Okay. So folks, this is a perfect time for you to get out and observe the sky during the summer. If you received a telescope as a gift during the holiday season and you've been waiting for an opportunity to use it, your opportunity is coming now. Don't forget those planets in the morning sky, and don't forget the constellations that we just mentioned that are visible in the summer sky as well. And the star map that we spoke of, stellarium-web.org, is a great one to help you find your way around the sky. And also, let me point out this thing, the Milky Way. This summer, as you're out enjoying your summer vacation, use your telescope and binoculars to scan through the Milky Way to see what you can find. The Milky Way has so much wonderful stuff to see. It's worth an hour just scanning through the Milky Way. And with that telescope, right in that region between Sagittarius and Scorpius, that region is rich with star clusters and other galaxies that you can look for using your telescope. Remember, clear, dark skies always work best for that. And this is a really good time to explore that region of the sky. So use your telescope for that, use your binoculars for that, and get outside and enjoy the evening sky. It's always great to be out under the night sky. It helps to give you a sense of calm, a sense of peace, and helps you to connect with the evening sky and to connect with the universe too. And remember, it doesn't matter where you are, wherever you are, you can get outside to enjoy the sky. So thanks for joining us tonight on our June 2022 edition of Night Skies at Home from the Franklin Institute Science Museum. My name is Derrick Pitts. I'm the chief astronomer, your cool astronomer, wishing you a great summer. Don't forget to come visit us at the Franklin Institute this summer. We have this great exhibit, Harry Potter, the Exhibition. If you've heard anything about this, you know it's the exhibit you have to see this summer. So make sure you go online, find out when tickets are available, and go check this out. You will absolutely love this exhibition. It's fantastic. I've seen it. You wouldn't believe the stuff that's in this exhibit. It's really fantastic. So make sure you come see it. We'll be back again next month. The first Thursday night of the month, July 7th at 7:45. We'll be talking about all things happening in the summer sky then. And we expect that there will be some interesting developments in the space exploration realm for heading back to the moon. So be sure to come back and join us then. We'll talk about that in depth. It takes just a few minutes for you to catch up with the night sky and get familiar with what's out there. So take a few minutes in the evening to enjoy the night sky. I'm sure you'll enjoy it. Thanks again. Again, I'm Derrick Pitts. You can follow me on Twitter. My handle is @CoolAstronomer, and come visit us at the Franklin Institute. Have a great month, folks. We'll see you next month. So long.